So this is part 2 of our discussion about polynomial and in x-axis behavior. So here we're given this polynomial, right? It is a fourth degree polynomial because it has a power of 4. Okay, sometimes those are referred to as quartics, right? So you can call it a quartic, or we can simply call it a fourth degree polynomial, right? That is fine to just call it a fourth degree polynomial. Okay, and it's telling us that x minus 1 is a factor, okay, which means what is the root? If you set your factor equal to 0 and solve, what does that mean x equals? Positive 1. Okay, so that's how we find your root, is by simply setting your factor equal to 0. Okay, and we can verify that from the graph. Notice here that it crosses the x-axis at positive 1. So sure enough, that is where we're going to have a 0 or a root at x equals 1, because that's where the graph crosses. Now if we notice, what is the behavior of the graph as it crosses? Okay, hopefully notice that it flattens as it crosses the x-axis. So a flattening as it crosses the x-axis has a multiplicity of 3. Okay, so this factor, right, if we were going to write this out in factored form, that would have a little 3 as the power of your factor, right? We talked about on the other video that the power of your factor is the multiplicity of that root. Okay, so we're going to do that sometime today in the future, but for right now, that's what it means. So as we come back to our problem here, or the given thing here on whatever, it says, how many times is is 1 going to be a factor? So to figure out how many times our root is a 0, we're going to do a polynomial long division. Okay, so we're using the coefficients of your polynomial, negative 1x to the 4th plus 1x cubed plus 3x squared minus 5x plus 2. Actually, we don't need to have the plus 2 there. Just needs to be a normal 2. Okay, so synthetic division, and we are looking for a remainder of 0. This is what we're hoping to get, as a remainder of 0. And however many times we can use long division, synthetic division, and get a remainder of 0, that's how many times this root is going to be a 0, right? That's the multiplicity. So at the end, we're going to count up the zeros and see how many times we were able to do it. Okay, so let's do it for the first time. So sure enough, it works out to happen once. And now we're going to do synthetic division again with just these numbers. Okay, we're not using the entire polynomial again. We're just using the quotient, and we're looking for a remainder of 0. And we see that we get a second 0. So now we're going to do it one more time, well, as many times as we can, but now only using these numbers. So we have a 1 on the outside still. We're using that same root over and over again to see how many zeros we get as remainders. And we get a third 0. So we're going to try it again with these terms right here, right? Just with your remaining terms. And when we do it for the last time, we see that we don't get a 0 remainder. So now we count up the checks. There's a blue one, a black one, and a red one. So it has a multiplicity of 3, okay, because that's how many times we were able to synthetically divide and get a remainder of 0. Right, that was that factor theorem from a while back. If the remainder is 0, then the divisor is a root. So describe the end behavior. Okay, so the end behavior is the graph flattening at that x-intercept. So the behavior is it flattens. Okay, so let's move on and see what else we have about finding zeros of a polynomial. In this case, it's going to happen numerically, right? So we're looking at the numbers here. So this is our graph that we have. That's this graph over here, this positive third degree polynomial. And it wants us to find some values from the graph. Okay, h of negative 2 and h of negative 1. So there are a couple of ways we could do this. We could plug negative 2 into all these x's, right? And you can evaluate it and get a number, or we can use the remainder theorem. And the remainder theorem says that when we synthetically divide your polynomial by any x value, the remainder is the y value, right? That's what the remainder theorem said from a while back. So we're going to use synthetic division because it's faster to see what the remainders are for all of these values. So we're going to do it for -2, we're going to do it for -1, for 0, and for 2. So I suggest that you pause the video and do all that if you're watching and taking notes. If not, I guess you're going to see the answers right now. So here are all your values. H of -2 is -9, h of -1 is 4, h of 0 is 3, and h of 2 is 7. Okay, so that would correspond to your values on the graph if we had a graph that was large enough to have all of them. Okay, but it says on the graph, clearly there's a 0 between -2 and -1. Right? Somewhere between -2 and -1, the graph crosses the x-axis. Okay? We're not exactly sure where, and we're not going to approximate it with a decimal. We just know that it does cross there. Okay? And then it says, explain how your findings leads that to this description. Okay? So what is the y value at -2? H of -2 was -9. Yes, would you agree? Is that on your graph? Right, no, we don't have a -9 value on your graph. And what about h at -1? That was +4, correct? So if I have, let me draw this again, if I have a -9 y value, and then I have a +4 y value, and the graph is continuous, what must happen between those 2 points? If I'm at -9 down here and I'm +4 up there, then what must occur between -9 and +4? Zero has to be in between -9 and +4. Okay? So that's what we're explaining. So numerically, there has to be a 0, because on the left side, it's a negative value, and on the right side, it's a positive value. And between any negative and positive, there has to be a 0. Okay? A 0 has to be there because it's negative on the left and positive on the right. So does that work for the 0 between 0 and 2? Okay? Does there have to be, based upon your numbers, does there have to be a 0 in between there? Okay, so we had a y value of 3, and then we had a y value of 7. Okay, so does that same reasoning apply? Does there have to be a 0 between 3 and 7? Right, what if the graph went like this? Does it have to cross the x-axis between a y value of 3 and a y value of 7? Okay, and hopefully you're saying, no, that's ridiculous, because of course not, right? Does the same reasoning concerning it hold true, right? Of course it does not. No, the same reasoning does not hold true. We have a y value of 3 at 0, and we have a y value of 7 at 2. So this does not guarantee that we have to have a 0 between 3 and 7. Just that all the numbers between 3 and 7 will be there. It does not have to have a 0 between that. Okay, so there's got to be another way then in order for us to find that 0 besides this whole idea. So let's put this down into words here on our next little, on the back. Okay, we want to make an inference, right? It's not a theorem per se, it's just going to be an inference. So what we notice, hopefully what you notice, is if we're positive on the left side, right, we have a positive y value at some x value of a, and then we have maybe a negative y value on the right side. If this is the case, that means for a continuous function, there has to be a 0 in between there somewhere. Okay, if you're positive on the left and negative on the right, then there has to be a 0 somewhere in between. Okay, so a positive on the left side of your interval and a negative on the right side of the interval means that there has to be a 0 somewhere in between there. Okay, or we could flip this lefty-righty. Okay, and what if we have a negative y value at A and a positive y value at B? Okay, that also guarantees that there's going to be a 0 in between there somewhere. Right? We don't know exactly where it's going to be, but it will be there. So if either of these cases are happening, right, we know what the y value is on the left side, and we know what the y value is on the right side of some interval. Okay, if one's negative and one's positive, then there has to be a 0 in between there somewhere. Okay, so it's either negative on the left, positive on the right has a 0, or negative on the right, positive on the left also has a 0 in between there. So let's see if we can apply this concept to our, our table here. Okay, so this table represents the values of a quartic function, so we know some things about it. Okay, first of all, we know that this is a quartic. So what is the power of a quartic? Quartic means 4th degree. Okay, so that should mean something to you in your brain. You should be able to picture what a 4th degree polynomial looks like. Okay, because we're assuming that you do when we say this question. So if the function has a negative root, right, a negative, so one negative root. Just one negative root. And two distinct positive roots. So we only have two positive roots, so positive, and like on the right side of the y-axis, and one negative root, one root on the left side of the y-axis. So let's look at our points here, and let's see if we can't make a little sketchy sketch of our graph and see what's going on. So I'm going to take the time over here to do this. Okay, at -4, we're up at +40. Right, so that's pretty high up on your graph. At -1, we're at -8. Okay, at 0, we're at -3. So that's your y-intercept there, 0, -3. At 1, we're at 0. At 2, we're at -2, so maybe in there somewhere, right? This is not an exact science. So at 3, we're at 5, down here. And then at 5, we're at 26. So 4, 5, 26 is in here somewhere maybe. And then at 6, we're way up at 90. So way, way, way up there. Okay, so maybe we can do a little sketch of our graph, right, and get a little idea of what's going on. It goes down, it comes back up. It hits at 0, there at 1, and then comes back down, and then goes way up like that. Okay, 4th degree, right? Both of our arrows are pointing in the same direction. Our end behaviors are both going up to infinity, right? For all 4th degree polynomials, your end behaviors are the same, okay? Which is why it's important that they told you that they don't turn around and go back down anywhere. They are going off to infinity on the left side and the right side, okay? So how many times does this graph cross your x-axis? Once here, right? Once between -4 and -1. Another time here, and a third time, right? 3. Like it says, one of them is negative, and 2 of them are positive. Okay? Which means, what can we say about the multiplicity? Okay, going back to multiplicity, if we have one negative root and 2 positive roots, but they have to add up to 4, one of those roots has to have a multiplicity of 2. Right? So that's where we get here with this graph. Notice that it bounces here. That's going to be your multiplicity of 2. This crossing is going to have a multiplicity of 1, and then of course this one will also, over there on the right side, have a multiplicity of 1. Because the sum of your multiplicities has to be the same as the degree. So 1 plus 2 plus 1, that's 4. We have ourselves your fourth degree or your quartic polynomial. Okay, so looking at the table, are any roots directly given to you in the table? Okay, and yes, this one right here is going to be a root. And how do we know that's a root? Yes, very good. Because it has a y value of 0. Right? Anytime we have a y value of 0, that's where it crosses the x-axis. That is called a root. Okay, the next question is about the multiplicity. So what did we think the multiplicity was at 1, 0? Right? We said that multiplicity must be a 2. Okay, graphically it bounces, right? When we drew that out there, we showed, or rather we assumed, I guess we assumed that it bounced. But look at the y values. On the left of positive 1, the y value is negative. And on the right of positive 1, the y value is also negative. Okay, and since it can't cross twice, that means it has to come up and touch and then go back down. Okay, so that's another one of your explaining your reasons, is that we have a negative on the left and a negative on the right. So a sign analysis also. So what about number 2? Between which two x values is the negative root located? Okay, so we're going to use what we did up at the top of this page. Between what two x values do you think? Between -4 and -1. Okay, so between -4 and -1. Right? Because what is the y value at -4? It's 40, so there's a positive y value. In fact, we don't even have to say that it's 40. We just have to say that it's positive. Right? That's the important part. And what about the y value at -1? Yes, it's -8, but the important part is that it's negative. So less than 0 is how we represent a negative value, and greater than 0 is how we represent a positive. Because it's negative on the left, positive on the left and negative on the right, there must be a y value of 0 between -4 and -1. Okay, so we're talking about the y values. The y value on the left was positive, and the y value on the right was negative. So that means there has to be a 0 in there somewhere. And we're going to use a similar line of reasoning to figure out where the second positive root, okay, between which two x values these are going to happen. Okay, so those are going to happen between +3 and +5, right? Because at +3 we have a y value that's negative, and at +5 now we have a y value that's positive. So we're going to use that same line of thinking, only we're going to flip these two things. So between +3 and +5, right? From our table, that's what we see, because at +3 we have a y value that's less than 0, so a negative y value at +3, and we have a positive y value at x equals 5, okay, a positive. So there must be a 0 between a negative and a positive on the interval from 3 to 5, right? So this is an x value of 3 and an x value of 5. That's somewhere in between here, there's going to be an x value with a y of 0. Okay, so that's looking at it numerically and using positive and negative values. Okay, so here's the key right here. If it's positive on the left and negative on the right, then there has to be a 0. Or if it's negative on the left and positive on the right, there also has to be a 0. Okay, so there you go. There's some more about intervals and polynomial end behaviors. So hopefully your homework is easy to do. Okay, bye.